welcome to this fourth webinar in our webinar series. So today we are joined by one of our Pathfinders, the Pathfinder 4, and we're going to be hearing all about FAIR data for the biomolecular simulation community. So today we're going to hear a presentation from James Gebbie and Jas Kalayan from STFC. So without further ado, I'll pass it over to James and we can get started with the webinar.
Thank you, Nikki. Hi, everybody. So today I'm going to speak to you about the work we're doing in our Pathfinder under the PSDI program. So the talk's going to be split into largely two parts. So I'm just going to give you a basic overview of what we're trying to do. And then Jas is going to get the fun and do the technical, how everything works, and do a technical demonstration of where we're up to so far. And then after all that, you can then we'll take some questions and try and answer as many as we can. So what is PSDI? I'm not going to talk too much on this. So the aim of it is to improve the practices of handling data within the EPSRC remit area. Obviously, biomolecular simulation has quite a lot of synergies with different research councils, but by far and large, most of us come under the soft matter theme in EPSRC, I think. So the aims is to improve the findability and accessibility of reference quality data, combine data from different sources, improve sharing of data, software models, deploy close to data computation, containerization, and even HPC in our case, enable AI to develop novel methodologies around more data sets than are currently available, and hopefully enable the teaching of researchers to make the results of their research open and fair. So they're the basic aims. In our Pathfinder, we focus purely on biomolecular simulation, but I must start by saying this. So we know that biologists in general are brilliant with data already. There's lots of structural biology data, particularly run by EBI and various other organizations, and these seem to all be focused around experimental data mainly. But there's a fantastic set of research. I mean, this is just a subset. There's lots in bioinformatics and other disciplines of biology. However, in our field, in biomolecular simulation, it's a bit of a wasteland of sort of previous efforts that we've been trying and things that are slowly emerging, but there's not much in the way of production databases that we can go and use today, at least within the UK anyway. So we've had lots of initiatives that have been tried in the past that have not worked out. This is largely not down to the platforms not being good. This is down to when they were doing it was probably just ahead of their time. Lots of things have happened, because these were probably tried 10 to 20 years ago. So hardware obviously has come on leaps and bounds since then. So, the disks that we used to have 10, 20 years ago pale in comparison to the multi-10 terabyte beasts that you can buy today. So there's lots of reasons why these initiatives haven't worked out, because we struggle in our field with our systems are both large, and we often run lots of simulation repeats and long trajectories, so our data sets tend to be quite big. So it's a difficult problem when you live in an era where storage is just not very good. So next up then is there's projects around. This is just a few of them. There's lots really around the world. This is just two that we've been interfacing with at the moment. So there's MDverse run out of Paris. This focuses on mining data from common repositories like Zenodo. So it categorizes MD trajectories and various files that are shared on those platforms into a single place. And then there's the new MDDB headed up by Modesto in Barcelona. And this really is designed to bring a lot of these big databases that are already existing in various labs and various institutions under one house. It's quite an interesting project. It's just kicking off. And this is really an interesting one for us to follow. So The difficulties with a lot of these platforms is if you're focusing purely on trajectories, it's very difficult to build in FAIR into that ecosystem, because actually FAIR starts as soon as you pick up the crystal structures and start moving forward from there. You should be recording lots of things that you do in this model setup, the model actual run phase, and actually the analytics phase that comes after that. So to be fully reproducible. And I personally have been on the end of this as a software methods developer for the last 10 years. I've been on projects where we've been developing software tools, and we've been given a paper as a start point, not data, a paper, and so and then we try to then build a software tool from the workflow that's prescribed in this paper, not even scripts. It's and we simply can't even just reproduce the observations in the paper. Just setting up and reparameterizing those simulations and getting the same result is really difficult sometimes. And so we've had that a few times. So if we can have all of this extra data available to us, it could improve quite a lot of things. But we'll talk about this more in a bit. And then there's all of these generic sharing platforms. So there's lots of them. Figshare and Odo is what most people are familiar with. Mendeley is another popular one. I guess in the US, I think is the OSF is the common one. I think there's some kind of grant terms or something over there now that makes them have to use something. These are great for sharing files. Great for getting persistent identifiers. There's no real requirement to share data that is fair, though. So if you share an archive that has a format that is fair within it, then it will be fair. But the thing is it's not required. It's not enforced. So we all know when we're busy and we're in that research publish cycle, we're not going to be doing these things. So basically, we're all left to our own devices there. So on to the main issues in our subject domain then. We've discussed some already. So these are the issues that our Pathfinder is aiming to tackle. So there's no real consistent approach to storing and sharing simulation data within the community. We all have different ideas on how it should be done. We all have access to different platforms, universities. Some of them all have really good provision for storage. Others won't have anything. It's the same story in HPC as well. It's a bit of a lottery. There's no real infrastructure or route to make simulation data accessible. So again, it's a bit of a lottery whether you've got access to these things locally. There's nothing nationally really. Usage of existing or emerging platforms is not fair. So this, again, this is about dealing with this findable. I mean, most of them will do F&A in FAIR actually, but the interoperability and reproducibility is the difficult part. It's a very big area that's actually quite difficult. The culture that we research, that we research in doesn't encourage us to do these things. We're all under time pressures doing our research. We're very much trying to get between grants, get the things done that get published, and then move on to the next thing. And we're all doing this. So it's not, there's nothing intrinsic in that culture really that forces us to deal with this. I think in some research councils that's different. So I think in BBSRC and MRC, they'll have in your grant, you'll have to write a data sustainability plan, probably alongside your typical software sustainability plan. But I think within the EPSRC remit, we typically focus on things like the software development sustainability plans, but don't really have to write very much about data, really. We could probably just say, we'll give it to people if they ask for it. Then the publications in the field, we have lots of publications with good supporting information, but these by themselves don't always let you reproduce what's been done. We've probably all on this call had experiences where we tried to do this and failed because You know, there's all these little tips and tricks that we do, you know, when we get the crystal structure, how we polish it up, various things that are missing, how we generate them. We all do it slightly differently. We all use different tools. And unless that's specifically recorded, if the postdocs no longer, you know, if they're working in a bank now and you can't get in contact with these guys, then, you know, you might as well give up, because you'll never know what tips and tricks that they did to get that result. So, and it's difficult to know exactly which experimental data set. So sometimes we see lots of people talking about a particular protein. We go on the protein database, there'll be several flavors of it in the PDB, for example. There might be things in PDB redo. We don't know exactly in some papers which one of those they've actually started with in the first place. So, you know, then in the analytics, we don't always know the exact experimental information that's been drawn in to draw the conclusions. So, you know, it's not all papers, it's just there's things. So, you know, how can we tease this out in a way that is complete, but without forcing people to go through massive cultural change? So this is really what our Pathfinder is really trying to do. So our objective really is to establish some kind of data infrastructure prototype and the tooling around that. And actually, at the moment, we're focusing around the tooling around doing it that sits within your environment, as Jas will talk about, to improve these data practices within our field without inducing major cultural change. Because if we try to get people to change things, we'll fail probably. You know, if it's massive. So, you know, we're trying to improve data practices and align with these FAIR principles. It's the main aim of our Pathfinder, obviously. We're prototyping tools to capture the full data provenance during model creation. So Jas will show you this, how it works, and a demonstration of doing with the early tool versions that we've got whilst you're doing simulation. We want to prototype infrastructure tools to store and access this provenance in the data set. So that's the F and the A in FAIR. The provenance capture is the R in FAIR. We want to establish long-term collaborations with other initiatives. So we've kind of already started this. So Jas went to a meeting yesterday with the MDDB developers, and you know, that by the sounds of it, that's been very productive. So we'll keep, you know, that we'll keep developing things around that space. Ultimately, what we want is something that's you know, beneficial for the community as a whole. So, you know, if something more joined up is an excellent way to go. We want to establish hard links to, you know, experimental data sources. So exactly which pieces of information have been used along that provenance web, if you like. So, you know, if you used crystal structures, which exact one went into that workflow that you used. We're not yet tackling interoperability. There's better projects out there that are doing this already. You know, we're not really going to try and reproduce anything that other people are already doing. It might be that we, you know, later down the line, we start talking to those people and bring these things together. So we really want our data to, you know, be easy. So our philosophy is that data practice should be baked into the way that we work. You know, you shouldn't have to change the way that you work too badly to do these things when we actually have the technologies to sit alongside you and bring this without inducing that massive change. You know, for example, if we're doing our research, you know, you've gone through all the hard work of doing the parameterization, you've done the run, you've done the analytics, you've drawn your conclusions, you've written a paper, and then you come to fill in a great big form that's got lots and lots and lots of parameters that how you know, did various things. You're not going to do it. I mean, it's the very end of the process. Some people will do it, you know, but not everybody will. Some people will partially do it. Some people won't bother. Some people will do it to completion. So we want to eliminate this process. We want to, this information, we ought to know about it as you're working with these data in your workflows as you're going. So our tooling is designed to harvest this data in an automated way. That's what we're doing. We do this in a way that avoids you having to change much about how you work, and Jas will show you more about this in a minute. you should always be in control of your data. So we believe that when you upload it to, you contribute it to whatever infrastructure we have in the end, that you as the data, creator should always be in control of this. It should be very easy to generate overviews of your data. So when we're talking about things like provenance, actually, it looks quite complicated sometimes. And when you're exploring these things, the tools can be complex. So what we mean by that is we want to have a really nice, accessible way to look at your, your data, especially when you've got a study where you might have, I don't know, 15 or more general simulations with repeats, and you're starting to look at this great big mess of the graph of how things connect together. So there'll be tooling around that. We're working on a lot more, but it's early days for us too. So a lot of this stuff is still under development. So what does all of this, what can it all enable? So we think that actually, improving the data practices within the EPSRC field will radically change the sort of landscape of what's possible. Because so if you look at what's possible in the other fields, like in the BBSRC and MRC spaces, I mean, the structural biology databases are basically what led to tools like AlphaFold. So I think in the EPSRC remit, we've always done really well with HPC and generating data, but we've actually not done very well with curating and storing and sharing data. So actually, we're behind in some ways. I mean, in some ways, there's other councils that do data very good, but behind in some ways with HPC, right? So, and again, that's something else that's being discussed at a very high level. As a research field, we can avoid duplication because, like we do with a PDB, you can go on there, has somebody run something like this. I mean, during COVID, we could have gone there. You can imagine we were looking for spike proteins. Everybody was going to DE Shaw Lab probably. There'd have been loads of them. Having our full data out in the open, again, it will enable other domains to exploit it. So, the obvious one is, people doing AI research, they'll be able to get access to very high quality data sets that have been tested against experiments, and they'll be able to develop tools around this. It might be particularly useful for people doing AI-derived potentials and things like that, or AI-derived force field descriptions and things. Having a big data set to test on could be quite cool. Obviously, collecting and sharing full model provenance will enable full reproducibility because you can see every single step that a researcher did to get from the very first input data to what came out all the way at the other side. And that's quite an important thing. Obviously, sharing this data over time, if we have lots and lots of different simulations using different codes, methods, force fields on similar systems, this builds up a sort of aggregate understanding based on different physics, and overall there's a statistical element to understanding that system, and this will improve the way that we understand the way that biology works. Sharing simulation data is obviously climate friendly because if you can already find a data set that fits what you need to know to go on and do something else, then you don't have to go on HPC and run these very energy intensive calculations in the first place. Or you might be able to start at a place that has less trial and error. So, it can increase the efficiency of the way that we do things. We can use high quality data sets to inform method development. So this is what I was talking about earlier about, improving the start point of when we're developing software tools. If we have access to models we can fully reproduce, we spend more time writing models and testing them and validating them against data that's good versus wasting our time trying to reproduce things that are difficult to do. I think knowledge will bleed between research groups, so you always get research groups on the cutting edge. If you can see how those guys are doing things, then that's going to lead to knowledge exchange. It really will. It'll be interesting for councils and funders to see the true cost of research. So, if we can see all the different data points from experiments come into simulations, you can see all the research teams and facilities that we use to create a piece of research. So really, I think there's some really interesting things that will come from doing things like this. So anyway, I think I've whittled on for long enough. I'm going to hand over to Jas. So she's going to talk about some of the nuts and bolts and show you some of the cool ways in which these tools work.
Cool, thanks, James. So yeah, I'll talk maybe a bit more about the technical side of things and the tools that we're developing. But first, just some shout outs to the people that have been helping us with this. So Kin is our industrial placement student from Imperial College London, and he's been helping us test the tools, find any bugs, so he can use our tools on his data sets that he's generating. And also to Joel, Tom, and Martin, who are part of CCP-EM, and they've been giving us some information as to how simulations could be used in the electron cryomicroscopy community, and what kind of information they would need from MD simulations if they were to use them. So a bit about the data that we produce. So as James said, we have like various steps to perform simulations, and we really need to be able to track all of these steps, but also we're producing quite a lot of data. So our trajectories, so this is an example of the COVID-19 spike protein produced by D.E. Shaw. We are saving these XYZ coordinates of these massive systems. So for each of the atoms, so we're looking at about hundreds of thousands of atoms in a system. We're saving maybe tens of thousands of frames or snapshots of our simulations, and they could take weeks to perform depending on what compute resources we're using and how big our systems are. So we're generating terabytes of data per simulation, really. And with all that effort, we need to be able to store it somewhere, but also be able to show easily how we've produced all that data. And we mainly produce a lot of this data on national infrastructure, and we get access to that national infrastructure via the HEC-BioSim consortium. So as I show here, there's various protocols involved in our simulations, and here's kind of just this sort of general, maybe 6 points that are the six stages for performing simulations. So as James said, we would get a structure from some database like the Protein Data Bank of a structure derived from experiment. I must say each of these 6 steps will be different depending on what you're looking to do. So they are 6 steps, but everybody will perform these 6 steps in a different way. So system preparation, it depends, your scientific question. Are you looking at a protein in a lipid membrane? So you might incorporate that into it. You want to solvate your protein at a particular pH, and all of this would use different software to do it. And then the next step, parameterizing, so adding the physics to how these atoms interact with each other and how they move. And that parameterization step will usually be done using the same software used to perform the simulation, but that's not always the case. So if you have missing parameters, you'll need to go down another rabbit hole of generating the parameters yourself. And then the last 3 steps, as I say, are generally done using the same MD engine. So your minimization, removing any high energy interactions between atoms, equilibration to the correct temperature and pressure, and then finally simulating. So I think maybe the low-hanging fruit are probably these last 3 steps, because they are using the same engine. And so we're developing tools maybe for these last 3 steps, but we want to then incorporate the whole provenance right from the start, as James said, to the end when we generate our simulations. So the tools that we are developing are using AiiDA, and AiiDA is a Python infrastructure, and it helps to track complex workflows used in computational science. And at the moment, AiiDA is mainly used in the computational material science. And what's quite nice about that community is that they usually can create a set workflow and apply that workflow to many different systems. The problem is in our community, that's not the case. We will have different protocols As I said before, you'll have different ways that you do each of those protocols. So you need a bit more flexibility and have the ability for people to record data in workflows that aren't set in stone. So we've developed aiida-gromacs, and it's a plugin for AiiDA. It's available on the plugin registry to download. So we're still developing it, and we've focused on GROMACS for now because 70% of HEC Biosim users are using GROMACS, but we want to develop a suite of plugins so that as many researchers as possible can use our tools to collect provenance. So I thought I'd go into maybe the basics of what AiiDA kind of wants from the user in order to track the provenance of their protocols. So 4 general things that you need is, what is the command that you want to run? Where do you want to run the command? And what are your inputs for the command, and what are your outputs? So if you know these 4 pieces of information, AiiDA is a good tool to use to track provenance. And when we perform simulations in our community, we do mainly do this on the command line. So AiiDA is a good tool for doing this. And what we've done is to try to take away any sort of change in how a user will use our provenance tools to how they wouldn't. So this is an example of using aiida-gromacs for a particular GROMACS command. And the only difference for the user is they have to include this underscore to track the provenance of this command. And here's a visualization of what that provenance looks like. So here's what the command is that you run, the input for that command, which would have been the PDB file, and the outputs from that command. And also in blue is the code that you use to perform it. Now, we also know that there might be some commands somebody might do outside of GROMACS, but they still want to be able to record that. So we've included a generic MD tool. And so this is the exact same command as before, but it's a bit more verbose in tracking the provenance for it. So this is what it would look like to track the provenance of PDB to GMX using generic MD. So you need to provide the command, the inputs for it, the outputs, and then the code, and then you can generate the provenance for it. So it gives the user a bit of flexibility who want to track their provenance while they're running GROMACS commands, but they might decide to change a PDB file by hand, and then they can track that change in the file using the generic MD tool. So this is what it would look like then if you performed an MD simulation, a minimization using aiida-gromacs. So we have the 7 stages and a visualization of what that provenance graph looks like that is generated in the background for a user. So how we would envisage this to look for people to use aiida-gromacs is to create a virtual environment and install AiiDA and our plugin. And they would then be able to run GROMACS commands if they wanted to remotely or on their computer. It's kind of up to them, and then be able to upload their provenance via a web interface. So here's a sort of breakdown of exactly how installing and using aiida-gromacs would work. So you'd create your Conda environment, you'd install AiiDA and our plugin via Mamba and PyPy. And for each project that you want to track the provenance for, you can create a new project using the Verdi command line interface that is built into AiiDA. Once you've done that, you need to start an AiiDA database and a daemon in the background, and then you can start running your commands. So you'd run your commands, and once you've completed that, you can save your AiiDA archive file and then share that with others or share it onto an online database. And yeah, so at the moment, we don't have a place to share these AiiDA archive files, but it is our aim in the near future to have a prototype for people to try testing the ability to share this data. And so we have a prototype where we will have a database that people can upload their AiiDA archive files and their trajectories to. So we'll have this all containerized, and people can upload their data and then also query the data that's been uploaded, and hopefully visualize as well with tools created by us. And I think I'll move on now to a demo of using aiida-gromacs, and hopefully how easy it is to use and how similar it is to actually using GROMACS. So I will load this up. So we have a tutorial for recording data provenance with aiida-gromacs. And as I said before, you would first need to load up the AiiDA database in the background. So we have a bash script that's written out for you. So you can load your AiiDA database, the RabbitMQ server, and the daemon in the background. So once that's complete, so this tutorial is a mirror of the lysozyme tutorial on the GROMACS website. So the only real difference is you can check and see how your commands, if they've completed running using the Verdi process list tool. So at the moment, we don't have any processes that have run, but we'll start off by running the PDB to GMX command. And then check that it has completed. So you'll see that the files return for the command as it would do if you were to use GROMACS without our plugin. And then we can solvate or create a box first. And we can see that the process is complete. Solvate. And then again, track can see that our processes have completed. And then add ions. So hopefully this sort of illustrates how easy it is to use and how similar it is to use if you were just using GROMACS. And again, so the adding ions section, that's completed. And then the last step that I wanted to show is the minimization. So that's complete. And then the minimization step. So we can check to see how that's going. So we can see it's currently running at the moment. And let's just check if it's finished. So it's still running. So if we look at the minimization, we're running 5,000 steps for minimization. So it'll take a bit of time, but it should hopefully be complete in a few seconds. It's still running. But once this is complete, there we go. So we can see that the process state is finished and it's 0. We can then generate a provenance graph just to visualize all of these steps and how they link together. So if you change you can just add the primary key for that particular process that you've run. So the last process that's run, so 47, using the Verdi node graph generate command, we can output the PDF file that shows you the provenance, and that should pop up hopefully in a few seconds. There it is. And so all those commands that we'd run on the command line, we can see then the provenance behind it and how the inputs for each of the commands link together and how they're used for subsequent commands and how they might have been edited first before they're used in another command. And then lastly, you can bundle up all of that provenance into a single AiiDA archive file. So this is in the SQLite format, and it's a compressed format. And this file can then be shared. And we hope to share like future tutorials on loading, querying, and displaying the data from these archive files. And in our web interface, we hope to be able to do that online as well. So I think that is me done. And I guess we've got if there's any questions for me or James.
I would say anybody who wants to try and break it, then that's good. We're pure software developers at the end of the day, so people trying to play with it, break it, find out where it doesn't work is probably more important to us than it just working out just fine. So I think we obviously have a roadmap for how these things are going to develop. It's not feature set complete just yet. I guess PSDI is not targeting operational phase until 2025. So, we've got some ways to go yet, but please do test it, break it. You can come to us on GitHub. We have an issue tracker. We've got email addresses. You can just come and talk to us directly, whatever's best for you.
Yeah, definitely. So when I think of using provenance tools, it's not just about remembering what you've done maybe a year from when you've done it, but it's also to show people the right way to do something. And if you have this provenance of visualizing how these steps are performed and what the right way to perform them is, I think that's only a good thing. So definitely something for teaching is a good idea.
AiiDA does have some HPC related stuff built in, so you can keep AiiDA running locally and stage off simulations. We all know that the two-factor authentication is an absolute pain. So the other thing is we have our own job submission engine, which is way more intelligent for molecular dynamics simulations than AiiDA actually is. So the current thinking is we might go and combine the stuff we have in Longbow with AiiDA as part of their transport protocol plugin framework, and because so we have the prototype in Longbow now for defeating two-factor authenticate. Well, not defeating it because that's the wrong way to look at it, but okay, we can store all the required information on disk encrypted to automatically go through the two-factor authentication. So, or you can just run it completely locally on the HPC, because this is not, the provenance generation steps are not compute heavy. I wouldn't recommend doing minimization steps and things on the head nodes, but it depends on the architecture, really. But yeah, so it's built in. We aim to improve the HPC and even cloud as well. We aim to look at that and improve the way that it interacts with other compute platforms. I guess I can just add, Nikki, phase 1A of PSDI was this very thing. I was testing and benchmarking AiiDA versus running locally and various things on HPC, right? So we kind of have stuff for doing that. We've just not built it into the release tool yet.
And just to add that, so the MDDB project has to be fair data as well. So they are working towards that. Just to put that out there. I'll just add, so I'm currently working on a plugin for Amber at the moment. So if you use Amber instead and you're interested in using this tool, then yeah, feel free to send us an email to register your interest, because we'd like to have people trying this out and breaking it.
Okay, so I don't think I see any more questions, but I think there is plans, I think, for future webinar presentations specifically on this when there's more development that's been undertaken. But I just want to say a massive thank you to both James and Jas for coming along and presenting their really interesting work, and to all our attendees for coming and listening. I hope you got a little flavour of some of the things that are being worked on, and do feel free to get in contact with us to get involved with what we're doing, trial out the tools, provide some feedback. That'll be really, really useful to all of the team, and keep an eye on our website for any future events in terms of webinars. Thank you, and I hope you all have a lovely rest of your afternoon.
Thank you.
Thank you.